polynomial functors in Lim 4. So, yes, so what are they? And two, why do we care about them? So I'm going to answer the second question first. So this is the why question. So polynomial functors were introduced by André Joyal as a categorification of usual polynomials. And since then, has been a lot of research about them, and they have become a very important tool in category theory. So I'm going to just drop a bunch of names. Citations are not going to be complete. Hopefully people who can forgive me if something is not, some citation is not complete. And obviously I'm not going to cite every work that has been done about polynomial functors. These works are mainly the kind of things that I'm expecting to formalize in this repository.
I put a bunch of references in the repo in one of the files, but I think I put them in the wrong place. I'll move them to the README.
Oh, great. Are they pushed now to the?
I pushed them to the wrong place. They're in one of the files as a comment, but instead I'll put them in the README. That's a better place for them.
Great, thanks.
There's a list of 10 references there.
Oh, excellent. So maybe the first work that we care about is by Gambino and Highland. So Nicola Gambino and Martin Highland wrote this paper called Well-Founded Trees and Dependent Polynomial Functors. Where they obtain W types, or the type of well-founded trees, as initial algebras for dependent polynomial functors. So by now this paper is a classic. So if you have not heard of W types, or types of well-founded trees, maybe the simplest non-trivial example would be just a type of natural numbers. And there's a polynomial functor that goes from set to set, or type to type. I'm also not going to distinguish between set and types because we are in Lean. So this polynomial functor sends x to co-product of 1 being the terminal set or terminal type. So this is unit type in Lean, plus x. And this is a co-product in the category of sets. You might see this as an option type of x. And an initial algebra for this polynomial functor turns out to be the fixed point of this polynomial by a lemma that Lambeck proved in the 60s, I guess. So being fixed point of P means P of x is equal to x.
Equal?
Well, we are in set, so that's isomorphism, but I'm just trying to be a bit suggestive, but this is an equation, really. I see this as an equation. But, okay, so since Kevin, to make Kevin happy.
Well, I think it is something that.
He's thinking in your heart.
Yes.
So this is 1 plus x. And the solution to this turns out to be natural numbers. So natural number satisfies this solution because the map that goes from 1 plus n to n formed by, so you're having a map from a co-product to natural numbers. So you have to give like 2 maps, one from 1 to n and one from net to net. And this you can form by 0 constructor and successor constructor. And this actually is an isomorphism and satisfies this equation. So this is the simplest kind of, natural numbers is the simplest kind of well-founded tree that can be obtained as initial algebra to this polynomial functor. So there are more complicated ones, but I thought like maybe it's this is for the purpose of my point. Okay, good. So that's maybe the first reference. That's 2, 1. two polynomial functors are useful in semantics of intuitionistic linear logic. So one particular such semantics are obtained by polynomial functors. This goes back to Girard. Excuse my French pronunciation. And of course, many other people have worked since then. I don't know all the references. Gambino Park also have made some related work. Okay, so that's cool that two seemingly separate things are related to polynomial functors. I'm going to write point 3 in the next. In the same column. Is this visible enough to everyone? So there are these things called generalized combinatorial species, which I think is also due to André. I'm not going to talk about items like 3 to 7 here. I'm just dropping a bunch of names. If you have seen them, good. If you have not, then you might learn about them later. Then we have semantics of dependent type theory can be obtained via polynomial functors. So this is due to Steve, and it's called natural models of dependent type theory. You can ask Steve about this if you'd like to know more about it. If you come from a more computer sciencey background, you might have heard of containers. Containers are very useful stuff in computer science, in semantics of programming languages, and they're basically polynomial functors. There are these things called topic sets, again due to Anders Real. So this is due to Altenkirch, I believe, and collaborators. The topic sets are Real and others, Finster maybe. Then there's opret. And then there is categorical dynamical systems. Can be modeled by polynomial functors. And this is due to Spivak, David Spivak, and many other people. Some of them sitting here from the Topos Institutes. Polynomial functors are big in Topos Institute. There's been a lot of dynamical systems and others, cool applications of polynomial functors. Coming from there.
In fact, I think, doesn't Spivak have a website with a bunch of polynomial functor stuff? I think that probably could have just cited that, not about everything.
I was looking for it. I'm sure it exists. I couldn't find it, but I'm sure it exists.
Okay,
You mean the book? Because she has a book with Nelson.
I have a book, but I thought he was maintaining a website with all kinds of polynomial functor research.
There's the workshop too, perhaps that's what you mean?
Yeah, there are several workshops.
There are 2 workshops, right?
Yeah.
There are 2 workshops, exactly. I have to say there are different notions of polynomial functors which are interesting to category theorists. For example, some come up in good-Willy calculus. The Taylor series of polynomial functors. That doesn't fit into this.
There's the Tamara von Glen
Right.
and Sean Moss version,
Right.
which actually is connected to dialectica, so, kind of.
Okay, interesting.
It's Leaks 2018.
Yeah, I pushed it to the README. I got that.
So you're saying good-Willy calculus of functors, that polynomial that appear there have some connections to this notion. Great. Okay, so now I'm going to focus on the first question.
I had a little question.
Sure.
I guess. So there's some research that I did with Jeremy a while ago on polynomial functors in Lean, but just for type. And I'm wondering like how many of these depend on polynomial functors that are not just, you know, like your example here was set in sets, but like for polynomial functors that are not in sets. Like,
interesting. I actually became aware of this quite late, just last week, this work. So I was talking to Wojtek Naruki, and he was telling me that Jeremy and Mario and others.
And Simon Hudo.
I see. They obtain, for example, co-inductive types as quotient of polynomial functors, if I'm not mistaken. So it would have been very useful to me if I discovered that before. I should have talked to you more. I mean, so it's more than co-inductive types, though, right? You can tell maybe.
Yeah, I mean, it was about quotients of polynomial functors, and the idea is that quotients of polynomial functors are a category that allows you to do quotients, inductives, and co-inductives. Okay. And this is really powerful because it means that now you can have like an inductive type which contains quotients inside of it. Like you can naturally construct set theory sets, right? Where it's just sets instead of like quotiented up to ordering or something like this. And then you can have, you know, mixing inductives and co-inductives and so on. It's based on the work that's done in Isabelle for the data type constructor for inductive types. Uses there it's called bounded natural functors.
I think we actually discussed this over lunch about the Isabelle, but you didn't tell me about the Lean. Okay, is this implemented in Lean?
So some of in Lean there's like the basic infrastructure stuff is done, but not like what we really need is like a tactic that will actually allow you to have an inductive command and that will auto-generate like the map. Like, you know, there's in your example you say, oh, it's like the least fixed point of 1 plus x, but you really want some tactic that allows you to write down something that looks like the definition of nat, and then converts that into, oh, you care about 1 plus x, and then you get this encoded thing saying that I have a morphism from 1 plus x to x, and then pull out 0 and successor, and then make everything.
That's very cool. So that means we will have in co-inductive types in which we still don't have.
So like Lean does not have co-inductive types, and there are no plans of adding co-inductive types to the kernel, and so the plan is basically to use something like this in order to get those co-inductive.
Okay, I'm interested in this because personally I'm interested in formalizing omega categories in Lean, and one way to do omega categories is through co-inductive types. And so that would, I definitely welcome if.
Yeah, but one thing that it definitely doesn't give you is like, it's not a category theory construction, right? It doesn't use the category theory library at all. And it's really just specialized to type in the same way that like the monad category or the monad type class is really just about monads and type, and then you have to completely write, you know, some other monad thing if you want the literal monads that occur in category theory.
I see.
So that at least is my impression of your work, is that it's really the categorical version of polynomial functors. And so that's why I'm interested in like, well, how many of these really essentially depend on interpreting polynomial functors in more interesting categories?
Very good question. I mean, lots of them. For example, natural models of dependent type theory. I mean, dependent type theories really, right? Because it can be having more constructors, but you can like model sigma and pi types using polynomial functors. I mean, some of them are functors from groupoids to groupoids, like combinatorial species, and some of these works are for higher categories and higher groupoids. For example, the example of upright, I should have mentioned here, Joachim Koch and Hausdorff. So yeah, I mean, these are in infinity categories, essentially. So yeah, not all of them are in the category of types. Okay. Okay, what are polynomial functors? So let's start from usual polynomials. So I'm going to do this usual presentation of polynomials. So let's say I have p of x, which is finite sum of exponents of some variable x. And these alpha i's are natural numbers. Okay, so for example, you might have 1 plus x squared. So I'm going to, at least for the first step, categorify this expression to a functor from sets to sets or types to types. Because sets turn out to be the nicest category we know. I mean, if we want to categorify something, maybe we should start from sets.
You want that thing to multiply the x's, or is that being deliberate?
So if they are, so I'm just for now considering like natural number coefficients for polynomials. So if like you have x plus x, that's 2x. Right, so what sort of data is actually encoded in here? Well, the fact that we have k, so this should on 0, natural numbers on 0. There are k monomials here, and I should record also their exponents. So that's all the data that we care about. So then let's have a type B for the type of monomials. Or this records like the k monomials essentially. And then we have an index family or dependent type E, which depending on which monomial you are in, like 0, 1, 2, or whatever, gives you the exponent. So now because I'm categorifying from natural numbers to types, everything is a type. So this guy is a type. And E is going to be from B to type. Okay? So another way to so basically you have a type family. That's a polynomial. Right? And another way to understand this type family, which will be crucial later, is to think of it as a bundle of sets or types. So E and B are sets, and P is just a map between them. And the fibers of this map are going to give you this family E. So basically, E of P is inverse image of P at B. Okay, good. So how do we categorify this example, for example, e.g.? So here, 1 plus x squared, the family that represents that is going to have a type with 3 elements as the base, so that's fin 3. So those are monomials. And now I have to give you the exponents or the arities. And the type of arities, so this is dependent type of arities, also is going to be fin 3. So here my monomials are 1x x squared, and so 1 is x to the power of the 0, or 0 here is empty type. So the fiber of this is empty, therefore I don't have any element above 1. This one, the arity is 1, so that's going to have 1 element as its fiber. So I'm going to just write maybe x1 for it. And here, this has 2 arities, so I'm going to record the instances of that. So that's going to be x2 and x3. So these 2 elements is mapped to this monomial, and this one is mapped to this one. And nothing gets mapped to 1. So how do we get a functor out of this? Where would be a good place to write? Maybe here. I don't need much space. All I need is like, out of this data, I want to get a functor. So I'm going to denote that by P of little p. It goes from set to set, takes a set X, and returns this sigma type, indexed by B, and sums over, well, X to fibers at EB. And this is basically my shorthand notation for the type of functions from EB to X. And this will be a set or a type. So this is not just a function, it's a functor. If you have a map from X to Y, F, then you do get a function from P of X to P of Y. So let's think about what is an element of P of X. Element of P of X is a member of this sigma type. So it's a pair with B and a function from EB to X. So that's going to be B and little e, which goes from EB to X. And now I want a term of P of Y. I'm going to have the same monomial B and change the arity by post-composing with F. So that's going to be F of, which will go from P of B to Y. And you can check that this specification indeed is a functor, meaning that it preserves composition and identity.
So P of X is everything that you can get as PP of X or something. The capital P of X is everything that's obtained as one of such components.
Right, so capital P of X is this bit. It's the sigma 2. So this is, for example, capital P of X for
P of 1.
this, exactly, and the bundle here would be fin 1 to fin 2. So this has 2 elements and this has 1 element. Okay, so this is, we covered one variable polynomial functors from set to set. There are 2 ways to generalize this. One is to consider multivariable polynomial functors, where you have more inputs and more outputs. And the other one is to go from generalize from sets to a category which has enough structures that you can express this sum. And these are so-called locally Cartesian closed categories. So I will come to that in a moment. How much time do I have? Good. So maybe I do multivariable polynomial functor from type to types first, and then we go to local Cartesian closed categories. Maybe I'm going to erase this bit. Okay, this is the first time I'm erasing something. Hopefully this doesn't go bad.
Maybe before you erase it, just while you've got the thought present in your mind, it's good to think about what the algebras are for these functors, because you put an example over there of the natural numbers, and you said that's the initial algebra for that functor.
Right.
And that's going to kind of come up later if you do W types.
That's right.
If you mention it, you might say what an algebra is, like for one of these polynomial functors, it's a set equipped with a map back from P of X back to X.
Right.
And so in this case, it's like a group structure on the set, although it doesn't have the group laws. It just has a numbering operation, a unary operation, and a binary operation. It's like,
Right, so this is very weak, so I'm going to choose another color. So,
Shouldn't store them in the down there. It's too wet there.
okay. Is it better still here? Okay.
You should not store it there.
I see. So yes, exactly. So let me just write down what Steve said. So if we categorify this functor, 1 plus x squared, through this process, what we get is functions from the empty type to type x plus functions from unit type to x plus functions from fin 2, which has 2 elements, to x. And so x to empty is basically the exponential reduces to 1. X to unit is just isomorphic to x. and this is x times x. So this is isomorphic to this one. An algebra for a polynomial functor is a map from P of x to x. If you are with polynomial monads, there are a bunch of equations it has to satisfy, but we are just doing algebras for polynomial functors. So it's just a map like that. So a map like this to x, since we are mapping out of a coproduct, is equivalent to 3 maps. One that gives you a map from 1 to x, so that's a constant, x0, let's say. A map from x to x, that's an unary operation, I. And I also have I get a binary operation, alpha. So it's a bit like group, but group has more stuff in it. And of course, if the coefficient here was like 2x squared, then you would have another binary operation. So maybe you would get rings, something like that, like at least a signature of rings. Okay, so now multivariable polynomials. Yes.
Sorry, what are the operations of this subject?
Oh, yes. So what's the question?
I would like to understand the operations of this algebra. So you have an algebra that consists of some relations with related sanities, and now what are the operations you can do? You can add them, you can do
Polynomial algebra is just a structure for a signature. So it's
there
a
are
set
operations.
equipped with operations of the corresponding areas.
Oh, I see. So these are the operations actually. Of the,
Yes,
They're not the elements.
that's the operations.
Oh, I see.
Of a certain signature.
Any other questions so far? Okay, so let me write an example of like a multivariable, just usual polynomial. So I might have like 4 inputs, w, x, y, z, and maybe I get 2 outputs, x cubed y plus 2, and 2x squared z plus y plus 1. So the question is, what functor corresponds to this polynomial? So to get there, we need an observation. From single variable polynomial, which is, how do I get this guy, or p of x in general, from the bundle description? Not from the data type description, but from the bundle description. So if I have that bundle given to me as a map of sets, then I can add these 2 trivial unique maps. So the one that goes to the 1 element set, I'm going to call it S, and another one T here, that also goes to 1. And I'm going to understand this variable x, which was here just a variable, and here just any type, as a type with its unique map to 1. Now I take the pullback of this map along S, so I get product of x and p. I'm still in category of types, so I use that product. Then I can push forward along p, so this push forward will correspond to having these dependent exponents. So I have this p lower star of x times p, together with, if this is pi, projection, together with push forward of that. And then finally, I have this sum over all monomials, and this was my type of monomials, the base type. So I'm going to sum over that p. And this is done by composing with t, essentially. I compose this map t with p lower star. So I get t lower shriek p lower star, and this was pullback operation, so that's upper star of x, 2, 1. It turns out, once you calculate all of this in category of types, this is basically the same thing as what I've written before, this one. So in category of types that are isomorphic. Now to go to multivariable polynomial functors, this 1 and 1, so 1 here was the fact that I had 1 input and 1 output. Well, what if I have more inputs and more outputs? I will have a type for them, and I still have this bundle. So now my monomials here in B will depend on type of outputs, and my arities also depend on type of inputs.
Yeah, put the P.
Maybe you shouldn't put the P
Oh, sorry.
there, yeah.
Very confusing, sorry. Thank you. So I'm going to do the same procedure. So if I have x over I, that will correspond to a bunch of inputs here.
Wait, so what is that?
Or indexed by this x.
Yeah,
So this is like, so I'm just repeating this procedure here.
right, but what does x represent now?
Well, x doesn't represent anything, the bundle over I represents something. And that's a bunch of like a family of variables. Because like these are like w, x, y, z. I here is not really w, x, y, z. I is like 0, 1, 2, 4. And each of them indexes one variable. So now these are types. And I do the same procedure. I take the pullback here, push forward. So this would be p lower star of s upper star of x. And then finally, I take the, I compose the T. So to get some bundle over O. So this bundle is indexed by O. That means it will give me these things, the outputs. So I have an example here. Maybe I just write it down and say magically this is what you get if you do the procedure of pull, push, whatever. So the example is this. The question is what sort of polynomial functor you get out of it. So I have to write this expression. So this is no more true, because this was in the case of single polynomial functors, but what do I get instead of it? Oh, this one is the right one. So if you compute all of this in category of types, you get sigma over bj pi over e b. So this is the fiber of e over b. So this little b is in here over some j, and this little e is over b. X, that's s of e. So I push e toward by s, so I get something in I, and then I can write x of se, that has the right type. And you notice that, I need one more sigma over j to get over O. So you notice that if your type of O has only one element, and your type of I also has one element, so this sigma disappears. This B will be a single family, like a family that has a single element in it. So you will have just sigma B in B. And here, your E of B is not dependent anymore, because you have only one B to begin with. So this will be pi of E in E, x of S of E. Well, S of E, it's going to terminal thing here, so it's really just x. So this dependent product is in fact non-dependent. So it simplifies to E of B, which we had before. So you would get single variable polynomials from multivariable polynomials. Okay, and this is crucial when we pass to locally Cartesian closed categories, because we actually define this, and like this is the definition of polynomial functors, like this guy. And then we get single polynomial functors by setting I and O to terminal objects.
What does corresponds to in type theory, multi-level type theory, that do corresponds to relative or dependent well-founded sets and the well-founded trees?
The algebra, initial algebras for that.
Yes.
Yes.
They are relative dependent because they are definable from the.
Oh yes. Yes.
There is in extensional type theory, but also in intensional there is a work to do. It has been done also through Pietro Sabelli was here.
Oh, interesting.
Yes, and there is also a connection to topologies, because this well-founded trees has a topological meaning also.
Okay, I would like to talk to you about the topological aspects. I mean, I know for topological thing, like at least when you do it in topos theory, forming this pi is a big problem, because when you work with geometric morphisms, you don't have pi functor or pull forward. But maybe the approach that you mentioned is something else.
I'm surprised by this sum over O here.
Yes.
Why isn't it just like a family over O?
I'm sorry, this should be a family because there's no way that we take a sum. This should be just a pair. So what I wrote before was correct, I guess. So this is a family over O.
Well, the object, the domain of the object, you bundle it all up, then it's summed over O. It wasn't wrong, it just a different way of writing it, yeah.
Well, are you saying if there's another map to the terminal object? Like with the
No,
picture?
when it's indexed over O, the domain of the map is the sigma over the O's. He's writing it as a map over O, right?
As a map over O, this would be the domain of the object here.
Exactly, you still write that, and that object is that.
As a dependent, whatever. Okay, where are we? Oh, okay, so now I have to tell you how this is, like, if you work with, like, not category of sets, but like, so all of these operations are done in category of sets. I could take, pullbacks. So that's fiber product. I could take this push forward. This was pi that we have in types, and this is native to Lean, obviously. So you can do all of these things in Lean, and we have formalized this in category of types. And you can do certain operations on polynomials, sum them or compose them. That means like substituting one polynomial into the other. It's a bit more complicated in other categories to formulate that. But what sort of other categories we can do these operations? So that's where locally Cartesian closed category structure comes from. So let me give just a definition of that and justify why it works. Is it okay if I erase this bit? It's been a long time ago, this bit. Okay. I hope good enough. Okay.
It's great, because that buys it and makes it more visible.
That's the other side of it.
Yes. We'll teach you.
Yeah, sure.
I get it some, by the end, I'm sure I get it. So, locally Cartesian closed categories. So here's the definition. Maybe the simplest definition is a category C is locally Cartesian closed. If for all objects I in C on the slice category. Sometimes this is called over category, so slice or over, aka over. C over I is Cartesian closed. By which I mean you can form internal terms or exponentials.
Products. And products.
Yes. And products, yes. Cartesian, and the Cartesian product is closed. Thank you. Okay, so it turns out, so if you have this, for example, I can, because we have products or even pullbacks, I can take this pullback, and because it's now closed, I can also take the push forward. And sigma is always available because you're in a category and you can compose. This turns out to be equivalent to a triple adjunction. So if I have two objects I and O, I have this functor f flourish shriek, which if I have an object in here, that would be a map from X to I, because the objects of a slice are just maps to I. So let's call it, what did I call it here? Little x, maybe. So if I have X, then I can compose it with F. F is from I to J, sorry, I to O. These are bad choices, I and O, because I realized that this is not the same I and O. So F goes from I to J. And if I have some map from X to I, then I can compose it with F, and I land over J, which means I get an object in the slice in here. And you can prove this operation is functorial. Now, because C it has pullbacks, that comes from the Cartesians here, you get a right adjoint to this, given by pullback along F. And furthermore, the closedness assumption here means this will have a further right adjoint, F lower shriek, which is the push forward. This is the definition we take in our formalization. So we say C is Cartesian closed, locally Cartesian closed if this, first of all, we have this pullback functor and then that has a right adjoint. And we give the data of right adjoint. Okay, now I think I've said most of the things I wanted to say, if I have not forgotten anything important. Any questions? I want to show you the code before I end it.
What's an example of a locally Cartesian closed category that isn't the category of sets?
Okay, the slices of set. So there's a theorem that says if a category is locally Cartesian closed, its slices are also locally Cartesian closed. This we have also shown in the formalization. Actually, we have proved it using a lemma which says slices of slices are slices. It's called iterated slices. It's in MATLAB somewhere.
What's a more interesting example?
Category of pre-sheaves.
There we are.
So these are functors valued in types or sets. Are example of like locally Cartesian closed category. This is what Steve proved. So he showed that pre-sheaves are locally Cartesian closed. And so the reason is interesting because if I have category of pre-sheaves like over C, I'm going to write it humidity. I'm going to denote it by
Or a long pole.
so now the other side.
Now it's quiz time.
Ah, that's nice.
When I studied mathematics, there was a war between the professors of who had the longest.
Michelle, you're younger than I am. When I studied mathematics, they had people, staff, who would come in and do the board when the professor took a break between the two halves of the lecture.
For some professors, that was not often enough.
What about the students?
Yeah, when we were studying here, students.
So if I have a category C and take the pre-shifts over that, I just put C. So if I slice by some pre-shift, let's say P, P is a bad name, X, then somewhere in MATLib, this is proved to be equivalent as a category, so maybe actually not isomorphism, equivalence only, to pre-shifts over category of elements. So big hat for pre-shift, and I'm going to write category of elements of X here. And I don't know what is the MATLib notation, but usually we use this snake X for that. So this we know that pre-shift categories are locally Cartesian closed, or sorry, Cartesian closed. So this this is Cartesian closed, and Cartesian closed is invariant under equivalence of categories. So this will be Cartesian closed, and this is what we wanted to prove. We wanted to prove that the slices are Cartesian closed. So
pre-shifts are not Cartesian closed?
Pre-shifts are Cartesian closed. We wanted to prove them they are locally Cartesian closed, meaning that their slices are Cartesian closed.
What's the relationship between those two? Like,
That was the definition.
Is there a relationship between a category being Cartesian closed and being locally Cartesian closed? Does either one apply to the other?
Every locally Cartesian closed is Cartesian closed because you can take the slice over terminal. So if my C is LCC, then I take C over 1, that's isomorphic to C. This is the terminal object. So being locally Cartesian closed.
You're not assuming the terminal object?
Yeah, if you put the terminal object.
I said if you have terminal for this to be true.
Does Cartesian closed not assume terminal object?
We have locally Cartesian closed categories, not having terminal object, because I didn't say anything about terminal object, that are not Cartesian closed, I guess, yeah.
So they're Cartesian closed, which aren't locally Cartesian closed.
Oh, yeah.
Yeah.
Lots of examples.
Yeah.
Groupoids.
That wasn't a mathematical question, that was a notational. In algebraic geometry, if you're X, then you're locally X.
No. That's not how it works.
That's not how it works here, I know.
That's not how the terminology works.
I know, I've just discovered that.
I mean, in algebraic geometry, most of your properties are local. Closeness is not a local property in that sense. Like.
No. But you can have, there's a concept of a locally closed immersion. And closed immersions are certainly locally closed. That's the observation I'm making in algebraic geometry. X implies locally.
Path-connected space is not
I
locally
think
path
in many subjects.
Yeah, path-connected spaces are not locally closed.
Topology, when you call something
Where?
locally compact. If it's
So-
compact, it's locally compact. So
We have to. Thank you.